Okay, well, hello and good morning and happy Monday, happy week 10. This is our final stretch. So today I'll cover some stuff, and it's just like, I don't know, fun, just for fun, I guess. I don't know. Like, I won't test you on the stuff I show you today. Okay, so all right, so that's good, right? And then on Wednesday I'll go over what you can expect on the final exam, and then because that's coming up. So Wednesday we'll cover the final exam. I don't know, and I'll fill up the rest of class time with random stuff, I guess. And then Friday we'll take off. All right, so no class on Friday. Just, I guess, study or do something, So that's what this week will look like. So a little bit of content today. Wednesday we'll review what to expect on the final, and then Friday, no class. And I'll post a little link here. I do have a favor to ask, and that is to fill out your course evaluations if you have not done so already. And again, the two most important questions are the last two, which are like, what's your overall rating of the instructor, and what's your overall rating of the course? Of course, I appreciate whatever you are willing to give me regarding that. And they do count for something. So, every few years, every 3 years or so, we have like a performance review. and then, they go over, just different things, right? And then one of them being, your course evaluation. So they do count for stuff. I would say, because I've been here for several years now, like I feel secure in my job, but they're especially important if someone's like a new professor, if it's like their first year or second year, something like that. Your course evaluations do like factor in, into like whether UCLA will continue, working with this, professor or not. So not to make you feel like you're not allowed to say anything negative or something, because, if you feel like this person shouldn't be teaching at UCLA, then, you can express that. And that factors in. But yeah, your course evaluations do count for something. And so, I do ask your favor in filling those out. Okay, let's take a look at today's stuff. And these are just kind of miscellaneous topics. The 9 a.m. class, we got out a little bit early, so, probably something similar will happen here. And then, sorry about the daylight savings thing. But thanks for being here, huh? All right. Okay, so I wanted to look at Optim. Optim's a function, and I think we took a brief look at this when we looked at like Nelder-Mead, or I don't know, somewhere along the way. But this is kind of your general purpose optimization function that R uses, and I wanted to just show a little demo of like how you could apply it to a couple different contexts, and the examples I have are pretty simple, but you can honestly put in fairly complicated functions, even like say you could, and it's probably not the best way, but you could use Optim to say, find the parameters needed for a neural network, because a neural network is just at its core is just a complicated function with hundreds or millions of parameter weights to figure out. But at its core, it's just a function. You put something in, and it comes out with something else that says, this is a picture of a cat, or this part of the picture has a traffic light in it. Okay. And so the parts that are, the two most important parts are the par and the FN. The par is just, really the only important part about par is that you give it a vector, and the vector is the proper length, okay? And then kind of your starting values, if the starting values are closer to the actual value, then that's going to give you better results. So par is going to be important. And then function, fn, that's the function that needs to be minimized. And the first argument that goes into fn is going to be par, all right? And it's basically the vector of the parameters over which you are trying to minimize the function. And that is, and this function must return just a single scalar value. So if it outputs more than one thing, it's going to get confused, because the goal of Optim is to minimize whatever that single scalar value is, right? So it's going to output one number, and Optim is going to try to minimize that. There's a few other things that you could provide. So Optim's default method is Nelder-Mead, which works pretty well, but there are some limitations to it. And it also employs other optimization methods. Some are gradient based. So in 102B, you will learn about gradient descent, which is a very important optimization algorithm. You could calculate the gradient analytically. If you're not able to calculate the gradient analytically, then Optim is able to estimate the gradient using finite difference approximation, which is I think we demonstrated how to estimate the derivative by kind of just adding a small little actual h value of 0.001 or something, and then estimating the difference there. So Optim will do that, or you can provide a separate function that says, hey, this is how you're going to calculate the gradient and things like that. And so there's a few methods. BFGS, what is BFGS stands for? It's four people's names: Broyden, Farber, BFGS method. These Broyden, Fletcher, Goldfarb, Shano. Okay, so this is the algorithm, and I guess it uses something. All right, and it's pretty good, I guess. All right, and then I guess they modified it further, and it uses the gradient. But anyway, and that's that. Okay, and then you can also specify additional parameters and things. But basically, the two most important ones are par and fn. So how would you use it? Well, let's say here's a function, and you want to find, what is the value of the function that minimizes this, right? And I think we've seen this function before. But let's say, we've got x squared minus 2x minus 0.5x times y plus 2.5y squared. And how do we minimize this? Well, if you write your function like this, it's a function of x and y, that works in R, but it won't work with Optim, okay? Because Optim, it needs it to be a function that takes in basically one parameter, one argument par, okay? And par can be multiple elements, right? So par can have, two elements in it, and so to basically just convert this function into something that Optim can use, we take par, and we're going to say the first element in par is x, the second element in par is y, and now this function is going to work, okay? And so, because Optim is going to plug in, when you run Optim, you give it a starting vector of par. Give it two starting values, okay? And then R is going to look at that vector of 2 and says, okay, I got to manipulate these two values until I find the value that minimizes the output of this function, right? So it takes par in, two elements in par, and it calculates the value. And so this function is going to just return the output of this, one single scalar value, and it's going to try to minimize that. So here I just say, all right, run Optim, start off with some vector of length 2, and I just put in some arbitrary values. The function that we're trying to minimize is g, which is this function over here. And it runs. The default method is Nelder-Mead, and it gets these two values. All right. The true value is for x is 1.025641, and the true value that minimizes the function for y is 0.1025641. And we got values close, but not exactly that. 1.0255 rather than 1.0256. And then over here we have 0.10247 rather than 0.10256. Okay. One issue with this function is that near the bottom it's relatively flat, and so it kind of basically, it tries altering some of these values, and it didn't detect very much of a change in the value, so it kind of said, all right, we've reached convergence here, right? So convergence 0 means it reached its kind of internal convergence criterion, which basically looks for changes in this value and says, all right, we've minimized the value at least to some degree, in that, like, I couldn't figure out how to make this thing any lower, and that's that. Okay. If you use a gradient-based method, so I'm going to make basically the same call with par and function, and I'm going to just add another argument. Here I'm going to say use a gradient-based method. So I do method equals BFGS, all right? And here we get the values for x and y are pretty much exactly what they're supposed to be. So 1.025641, 1.025641, and then 0.1025641 and 0.1025641. But again, interestingly enough, a property of this function is that this region down here is fairly flat. And so if you look at this the optimized value, the output of the function at this location, the output of the function is negative 1.025641, which is exactly what we got, with the Nelder-Mead. So, this thing, it didn't exactly find the exact x and y values, but it found something, right around the correct value. And it's just, this is fairly flat. And so you can kind of like move a little bit in the x and y directions, and, the value of the function does, barely changes. And that's kind of what's going on here. And so, I'd say, it was successful at finding these things, right? Here it says like how many iterations it took. So for Nelder-Mead, it took 85. For the gradient-based method, it took only 17 iterations. Both of these, converged, which is nice. And for practical purposes, you will not notice a time difference between the 85 and the 17 iterations here. But I suppose it is possible that you have some kind of very complicated function where each iteration takes slightly more time, and you might feel a difference between something like 50 iterations and 200 iterations or something like that. But usually barely so. Okay. Here's another example, okay? This is a little bit silly, but I want you to think about linear regression, okay? And if we say linear regression is an optimization problem, what are we trying to optimize? What is the function or what is the quantity that we're trying to minimize in linear regression? What?
It's minimizing the squared errors.
Yeah, the sum of squared errors, sum of squared residuals is the quantity that we are trying to minimize in linear regression, right? So if you think of linear regression, you basically have these like two knobs that you can kind of alter. One controls the intercept, and one controls the slope, okay? And it's kind of like if you turn one up, and there's actually a fun little, I say fun, and I guess my idea of fun is so explained visually at setosa.io. They have this thing on OLS, and they have this thing where you can kind of these two knobs. One controls the intercept, and one controls the slope. And so, and this is an illustration of these squared residuals, right? So the fitted line is this line right here. The purple dot is the actual value, and so you can see the purple dot's really close to the line, so its squared residual is tiny. This brown dot is a little, kind of far from the fitted line, so its residual is big, and its squared residual is even bigger. But what I can do is I could say take the knob for intercept, and if I adjust it, right, what I'm doing is I'm pushing the line down, and so now I really shrunk the residual for the brown dot, but now the purple dot, the orange, and the green dots have big residuals, right? And so you can kind of see like, how do we do this, right? And you kind of you can slide the line up and down by adjusting the intercept, and you want to kind of hit, try to find the sweet spot where you don't have too much of one or the other. And you can also adjust the slope, right? And so you could make the slope real shallow, or you can make the slope real steep. So if you make the slopes shallow, what do you have to do? You have to kind of raise the intercept, okay? Or if you try to make the slope steep, then you have to kind of lower it, right? And so you have these two knobs that work in slightly different directions, and you want to try to find the right combination that minimizes the sum of squared residuals over here, right? And so that's kind of what we're doing. And I don't know in 101A, did you treat it as a minimization problem, or and like do the calculus to figure it out? Okay, I think you also do it again in 100C, all right? And you say, all right, and we're gonna do linear models and minimize this thing. And so, I don't know. So you can do that. Here we can, and then again, on the computer just uses LM, and LM just finds your slope and intercept that minimizes your sum of squared residuals. I wanted to, let me delete all of this stuff here. So here's my dots. My points are 1, 2, 2, 6, 3, 4, and 4, 8. And I can find the model, and I can plot the line of best fit. And this line has intercept of 1 and slope of 1.6, and this is the best fitting line right here. Okay. So again, silly to do this because we have LM, but we could treat this as an optimization problem, and we could say, hey, I want you to figure out the slope and the intercept that will minimize the sum of squared residuals. So let's look at this function that I wrote. This will be the function that we're going to use to try to figure out what the slope and intercept should be. And let me just show you the quantity that it returns, working backwards from the bottom of the function. The quantity that this thing returns is the sum of the squared residuals. So I'm going to do residual squared, and this is the quantity that we want to return. What is a residual? Residual is the difference between y and y hat. Y being a vector of the actual data values, and y hat being the result of plugging in our x values, our intercept, and our slope. So I'm going to get y hat by taking my current value for the first element in par and the second element in par. So this is my intercept is first element in par is b0, my intercept second element in par is b1. I use that to figure out my estimated values y hat, and then I just take the difference between y and y hat, and then I square those residuals and add them up, right? And so this is the function that we want to minimize, and we want to adjust basically the intercept and slope here. And so I throw this into Optim, and so here I started off with just arbitrary values. I said, what if we use an intercept and slope of 0 and 0, so not very good fits, and then we say, minimize that function of sum of squares, and what does it do if it successfully finds it? It says, hey, your intercept should be 1 and your slope should be 1.6, and it took me 15 iterations to figure this out, and we converged. So that's great. This is what we wanted, and it was successful. So it's a silly, again, it would be silly to kind of use this in real life because we have LM, but any other kind of function that you can think of, if you can frame it as an optimization function, this thing is going to work pretty well. We cover optimization quite a bit, in throughout the different courses because it is an important topic. But in like production settings, like this is going to frequently get the job done. Okay, let me give you your first 2 view quiz answers. We'll go ahead and give you your first 2. First one is A as an apple, and your second view quiz answer is E as an elephant. A as an apple, E as an elephant. Okay, let's look at another topic. This is again just a topic just for fun, I guess. Kernel density estimation. So kernel density estimation is the idea of, like, can we draw this curved line, right? The smooth line that kind of gives us a sense of what the underlying density curve of a distribution looks like, right? So it's like the smooth version of a histogram, right? So when so here, let me just show you. Here I'm going to just draw some 60 random values from the normal distribution. This is going to form my sample. And if I said, hey, what does your distribution look like? A tool that we have in our pocket is, let's make a histogram, all right? And so this is a histogram with a rug plot, and these little red lines on the bottom represent the 60 actual values. There should be 60 little vertical lines. Some of them overlap a little bit, but these are there's 60 vertical lines here representing the actual values that we drew, and here is the histogram that goes along with it. And so this gives us a sense of the distribution of our values, and we see most of the values are between 1 and -1, and the vast majority are between 2 and -2, and we get a few values outside of -2. I didn't happen to get any values higher than +2, but that's just because of random sampling. And so this is what it looks like. Okay, and somebody says, all right, can we estimate the underlying density? And so we would use kernel density estimation. And if I gave you this task, you would probably just draw a line, right? You would take your crayon, and then you just kind of like, all right, I'm going to just try to draw a line to kind of connect the tops of my histogram bars. And that's a pretty decent way to go. This is kernel density estimation. The computer does this, and this is what the computer draws, okay? And this is a pretty handy tool to have, just as kind of like a visualization tool. It just says, hey, does the underlying distribution kind of look like? Maybe it looks kind of like this. And one thing to keep in mind is that kernel density estimation is not going to give you a functional form of this, right? So a lot of times we see like a smooth line and we think, oh, there is some kind of mathematical function, or if I plug in a number, I'm going to get something out, and I plug in a number and I get something out. Kernel density estimation does not give you the functional form of that. It just says, hey, I tried drawing a smooth line, and this is what I drew. Okay, and it's helpful because sometimes we just want the smooth curve. Sometimes we want the histogram. Sometimes we want both. It's just to kind of give us a sense of what the underlying distribution looks like. There are some options you can kind of fiddle around with. And so with the kernel density estimate, okay, the option you can kind of mess around with is called bandwidth. And if I increase the bandwidth, it's going to like overly smooth out the line, or I don't know, overly. So now we get something that looks kind of like a normal distribution centered at 0, and this is okay. All right. Or I could decrease the bandwidth, and we get something a lot more kind of jagged. And these are all based on the same data. All right. Is one of these more correct than any of the others? I would not say so. Okay. Kind of like with the histogram, one thing you can do is you could change how wide your bins are, and even the positioning of the bins, which could make it look different, right? So if I decrease the width of my bins, this is what I get. And you notice that, oh, you know what? Having small bins is kind of similar to having a low bandwidth, right? So you can see the peak of each of these in the density curve also kind of corresponds to a location of a value, which corresponds to like where your little histogram has a line, right? And so these are all just different kind of options and maybe preferences that you might have as far as, what should my histogram look like. And all of these are based on the same data, and all of these are equally valid. I might have a preference, personal just preference for something that looks kind of more like this, but it's not like this is wrong. And I guess ultimately it comes down to what is it that I'm trying to communicate, and what visual tool is going to help me with that. Okay, I want to take a little bit of time and just talk about how does the computer make this kernel density estimate curve? Okay, and again, you don't get a functional form of this, but it draws basically these lines, and what it's doing is it's just doing a whole bunch of addition really fast. Okay, and so to kind of illustrate what's going on, here's a very silly scenario where I have 3 data points. My 3 data points are -1, 0, and 2. And in real life, you would never create a kernel density estimate if you only have 3 data points. It's kind of just a silly thing to do. But I think it does illustrate what the computer is doing when it sees data points and it's trying to draw, and we ask it to make a kernel density estimate. And basically, you could just imagine it just drawing like a normal curve, all right, centered at each one of your data points. Okay, so here I've got a normal curve centered at -1, a normal curve centered at 0, and a normal curve centered at 2. Here I set a very narrow bandwidth, and so you can see we have 3 separate normal curves. Technically, all 3 of these are being added on top of each other. It's just that for this normal curve centered at 2, the values over here are practically 0. Okay, and so when I'm adding this normal curve to this, I'm basically adding 0, and so I just kind of have there's very little overlap between these 3 curves. If I increase the bandwidth, though, all right, so here I've increased the bandwidth, and so you could see, the normal curve centered here and the normal curve centered here have a little bit of overlap, and so, it doesn't quite touch 0 here, right? So here I've increased the bandwidth to say 0.25, and so again, I'm basically plotting a normal curve centered at -1, okay, and then plotting a normal curve centered at 0, and then I'm adding them together. And so, where there's overlap, we get something like this, okay? And then same thing, plotting a normal curve centered at 2, and then I'm adding their values. And again, once you get down here, you're practically adding 0, and once you get up here, for the curve centered over here, you're practically adding 0, so it doesn't make a huge difference, okay? But as I increase the bandwidth, the amount of overlap, increases, and so, things start to smooth out, okay? Now, pay attention, again, it would be silly to do this in real life when you only have points at -1, 0, and 2, and having a bandwidth of 0.5. Now the curve starts to extend out to, -2 and +3 when, we don't have any values way out here or any values way down here. But again, it's just kind of the idea of you taking a normal curve, plotting it, taking another normal curve, plotting it, and then, just adding them together. And if I further increase the bandwidth to say 0.8, now there's even kind of more smoothing out, and we see, the 1 at 0 and -1, there's a lot of overlap, so you get this almost like one peak that's twice as tall, and then over here you have a peak centered at 2, okay? And again, it just kind of extends out, way further, which is, questionable. But this is kind of, these are all kernel density estimates with different bandwidth measures, okay? So these are all based on the same data of -1, 0, and 2, and increasing the bandwidth, kind of changes, what this density estimate looks like. Are any of these more valid or less valid? Well, again, we shouldn't be doing kernel density estimates for 3 data points in the first place. But these are all okay. It's just, it's questionable what kind of conclusions you'd want to draw, right? These are visual tools, okay? The default kind of curve that it draws and plots and adds up together is like a Gaussian curve. So you imagine a normal distribution centered at each value, okay? And it just adds them all up, right? So let me go back a bunch of slides. That's basically what it's doing here. It's just doing like a normal distribution centered here, normal distribution centered here, normal distribution centered here. And then we have basically like 3 normal distributions very close together. And so when they add together, they all kind of overlap and stack and they get really tall, right? This is like 2 points right here. And you know, all of these things kind of add together. And so you get kind of these peaks that add up, right? And as your bandwidth increases, you know, this is the default bandwidth, you know, there's just kind of a lot of overlap that you get this overall smoothed out curve, right? And so that's what we end up having here. Okay. Now there are other density curves, not density curves, different kernels that you could use. Kernel is one of those words in statistics that like appears in a whole bunch of different places, and like every time they appear, it's like got a different meaning. Okay. And so here the kernel is kind of like a little shape centered at this dot, okay? And we're kind of like adding these things up, right? There's other, you know, you've got these kernel functions that, you know, take higher dimensional things and turn them into something else. It's a different meaning. So, you know, I don't know what kernel, why we have to use the word kernel for everything, okay? But you have these different things. The default is a Gaussian, and that's probably going to be good enough for most cases. But if you wanted to have like a funny looking thing, sure, you could do it, right? So we have the Epinechnikov, which is just an upside down parabola, but you know, in math, whenever somebody does something and they feel proud of themselves, they want their name recognized, all right? So we have that, okay? And then we have the rectangle and the triangle and a cosine curve, or I guess maybe an upside down cosine curve. And here we go. Okay, so here are your upside down parabolas, and with little bandwidth, there's, you know, no overlap, and you have these 3 upside down parabolas. Something kind of funny happens when parabolas overlap. You get these little like nubs that show up, and so you have, you know, these kind of these funny shapes, all right, happening when you have these upside down parabolas adding on top of each other, okay? And here we go. We have, you know, 3 of these things, but then, you know, when they overlap, you know, you get these. It looks like little like snow mountains or something. So we have that, okay? So that's that. And again, we would never really do this with just 3 data points, okay? Here we have rectangles. Because of the way it plots, they look a little bit like trapezoids, but you can imagine rectangles. And, you know, if you have 2 rectangles overlap, okay, so they haven't overlapped yet, but, you know, when they start to overlap, now you get like, you know, these blocks that kind of stack on top of each other. And as they, you know, further overlap, you know, you get these, you know, funny looking shapes here, okay? With triangles, okay, when triangles overlap, when this side of the triangle overlaps with this side of the triangle, what are you going to get? You're going to get like a flat region, okay? So, you know, this goes down just at the same rate as this one's going up, and so they kind of cancel each other out, and you get a, you know, a flat region here. And as you increase the bandwidth, you get, you know, these little flat tops here, okay? And yeah, stuff like that happens, okay? And then here's the cosine curve. The cosine curve behaves a lot like the Gaussian, very similar shape, but, you know, the Gaussian technically goes off to positive infinity and negative infinity, so you have a little bit of a difference here, but as they overlap, you get this and this and this, which is quite similar to right, 22. This was the Gaussian, and here is the cosine. So these are the Gaussian, and then here's the cosines. Okay, so similar, a little bit different. The default bandwidth is determined by some formula where it uses either the standard deviation or the IQR divided by 1.34, and then it multiplies it by 0.9 and looks at how many numbers of points you have. There's some form. This is the formula that it uses. I don't know how they came up with this formula. You have one thing to keep in mind is that the kernel density estimate, just because just taking these shapes and then adding them up, a lot of times it will produce kind of tails out where you don't have any data, right? So we don't have any data beyond -1, but you get this big tail kind of going off in the negative side, which can feel weird. Like, for example, you could have, say, data from a Poisson distribution. Poisson distribution only produces non-negative values. You're not going to get anything less than 0, because it's like, how many times did something happen within this period, this window of time? How many occurrences of some event within a window of time? And so if I did give me a 100 Poisson values, here I can create a histogram, and I've specified the histogram so that the width of each histogram is 1. And I centered each. I had my first one start at 0, but if I did centered over here, I could shift this over, but I'm going to do 0.5 to 12.5, and that just shifts them over. And then we can add, say a density curve, and this is kind of what the density curve looks like. But again, the tail kind of extends off into the negatives, which is wrong, okay? Because we don't have any negative values, so this it should be exactly 0 versus and if I wanted to change the bandwidth of that, I could do that. If I wanted to actually plot the true density curve, what would I do? Let me do sequence from, say, 0 to 15. Phi equals 0.01, and then density will be d Poisson of, d Poisson, no, it's a mass curve. I can't do a density, so this is not going to work. Well, let's see, 0 to 15, do x, and then lambda equals 5. What does, there, I'm going to get a bunch of warnings, right? So basically I have to just do by ones. Okay, so I can have this, and then how do you plot a mass function in R? I don't know. I don't know how to add this to the plot. Let me do points, x, and density, and type. Well, let's just do color equals, let's just see what happens here. Okay, so this is the actual, these are the actual values. I guess the true, that's weird. 0, 1, 2, 3. Oh, this one's off the charts here. Let's make my wide limb sorry, I'm just fiddling around here. 0 to 0.25. All right. Excellent. No. doesn't like this. Why is this not working? Ylim. Some x not counted. -2 to 15. Am I doing something wrong here? What is my p? Okay, well anyway. It doesn't like it for whatever reason. Okay. Well, I tried. But yeah, just a word of warning. Sometimes the density estimate produces values out in the tails where there really isn't anything. Okay, well anyway, let me give you your last view quiz answer. Last view quiz answer is the letter B. B as in bear. And we'll just call it a day here. So on Wednesday, I'll go over what you can expect for the final exam. And then Friday, you'll have off. And again, I ask you a favor to fill out your course evaluations. And with that, we will see you on Wednesday. Have a good day.